Oceans have long been considered limitless places where human activities have little or no impact. Yet climate change, ocean acidification, unsustainable fishing practices, and pollution all threaten the ability of marine ecosystems to deliver valuable services. With threats to oceans increasing, new tools are needed to manage marine ecosystems. Establishing marine reserves where no extricative activities such as removal of species, oil, or gas is one tool to help alleviate many of the ocean's problems. At NIMBioS, the National Institute for Mathematical and Biological Synthesis, 4 early career scientists from around the world have gathered to determine optimal strategies for designing and managing marine reserves. They are also doing the same for nature reserves on land. The 4 scientists use mathematical modeling techniques to address their questions. Each brings different sets of skills to the project. Dr. Paul Armsworth is an ecologist from the University of Tennessee. Dr. Michael Bode is a theoretical ecologist from the University of Melbourne. Gareth Lennox is a postdoctoral student in mathematical ecology from the University of Sheffield. And Dr. Carl Taves is a mathematician from Duquesne University. NIMBioS sat down with 2 of the researchers to find out more about their project and how they go about determining optimal areas to be set aside for protection.
So I've got Michael Bode with me from Australia, but we've got scientists coming in from Britain as well as different parts of the US. All are early career scientists, so we've got PhD students, postdocs and new faculty who are moving into topics in mathematical biology. And we all have a shared focus and shared interest in how we can apply techniques from optimal control theory and constrained optimization to address spatial management questions and sometimes spatial temporal management questions in natural resource management and biodiversity conservation. So for example, how do we design marine reserves in a way that's effective for protecting marine biodiversity? How do we design terrestrial nature reserves to deliver biodiversity conservation on land effectively? Maybe it's how do we design contracts with private landowners so we can get biodiversity benefits in a cost-effective way that respects private land rights as well. And so all of these problems have this kind of common theme behind them of how do we get maximum bang for our buck invested or maximum return from a natural resource if it's like a fishery, and how do we design a management strategy that's most effective at doing that.
Okay. And with a focus on uncertainty, I think, in a way, I mean, a lot of these techniques are taken from different fields, but their applications in ecosystems and in conservation management has to take account of the fact that we don't understand a lot of these systems very clearly. So conservation planning, when it was first undertaken in a systematic way, was done by governments who had the ability to protect vast swathes of land all in one go. And so they tended to use techniques like integer programming, where they would select a subset of the land surface in an attempt to maximize the different aspects of biodiversity that are protected. But increasingly, conservation plans have to be enacted in a more iterative fashion, more dynamically. You can't purchase all the land you want at once, you can't protect all the species you need all at the same time. And that causes problems because there's uncertainty associated with what's going to happen in the future, the way that threats are going to evolve, both in and of themselves and in response to the actions that you take. And so, at first, the problem dynamically appears much, much harder. But we found that with the application of methods such as stochastic dynamic programming and optimal control, by incorporating a mathematical understanding of the way the threats are going to progress and the way the threats are going to respond to what we do, we can produce a schedule for conservation for how it will progress through time.
So in the working group, we're going to be looking at a set of different examples. So some of those are going to be tied to coral reefs and reef fisheries, some will be tied to tuna fisheries, but some are also onshore as well. The reason that a focus on mathematical biology is important here is that what we're actually after are not the one specific application. We're after the general techniques and results that are shared across these systems. And that's really a core rationale for bringing in people who are facing elements of this problem in slightly different ways in slightly different contexts. What NIMBioS is really providing to us, and it's a fantastic resource for us, we're individual scientists working in our own institutions on a common problem, a common set of problems, but often quite isolated. And so what NIMBioS is really providing here is a means to bring people together who have quite specialised interests, potentially in a university where they may be the only one who works on these things, but bring them together with other mathematical biologists who are facing the same challenges. But interestingly, they bring slightly complementary expertise, and particularly the applications they're working on raise slightly different challenges. And so it's a chance for real cross-fostering of ideas and expertise across systems that really there wouldn't be another way to achieve. One of the things that I find particularly exciting about the working group is the fact that there's a real capacity building element to this. We're specifically bringing together young scientists in this domain, and so there are relationships and the collaborations that NIMBioS is allowing to be built are things that can really grow over the coming years, because people are still going to work on these problems, but now rather than kind of pursue them individually and drift into very different veins, you will start to see more networked approaches and sharing of ideas that in this instance are spanning continents. So it's a resource as much as anything, a think space for bringing people together and giving them the computational facilities and the support that lets them really progress academic debates about these very specific applications in mathematical biology.
For more information about short-term visitors and how to become one, visit our website at www.nimbus.org.